Hey guys, we're going to talk about friction. So this is one of the subjects that you have to know about for the final. This is the effect of us having to have the same exam as the brick and mortar ITT course does. So we get to learn about friction now because it's on final. Just so you guys know, this is the hardest questions on the final have to do with this, but there aren't very many of them. I'm trying to cover it to actually give you guys a fair chance of getting these questions right on the final. So we all know what friction is. It's resistance to slipping. Resistance to slipping. So we know that rubber tires on your car are fairly grippy. There's a reason they're made out of rubber and not plastic, for example, or something else that's lubricious like Teflon. And the way that we characterize numerically something's resistance to slipping is this character mu. This is the coefficient of friction. Mu is a number that tells you how much friction there is between two surfaces. So mu doesn't just depend on one surface. It usually will be given like steel on oak, or iron or brass on concrete, something like that. There are tables and tables and tables of these things in certain books that you can look up if you have to. To give you an idea of typical ranges for mu, most things are going to be between 0.2 to 0.8. This is typical. Crazy car tire, rubber, top fuel dragster stuff can get upwards of 3 in very special conditions, but this is absurd. You'll usually never see something as high as that. Usually nothing much above 1. If you have oiled Teflon on oiled Teflon, you might get like 0.02 or something stupidly small. So what does that actually mean? Let's start out with an example of pushing a block on the ground, which we know is harder when the block doesn't have wheels because of friction. We're pushing with some force on this block. We'll say that mu equals 0.3. And we want to know with what force it takes to push this block. So the block, say, weighs 100 kilograms. And there's, 100 kilograms times gravity force downward here. Let's look at all the forces that are on this block. There is the gravity force, mg. There's what we call the normal force. This is Fn, or N is for normal. This is perpendicular to the ground, so I'll write that out. Normal force is perpendicular, that's what that sign means, to the surface. This is the force that keeps, matter from passing through other matter. So if you push on something, it's the normal force that keeps my fingers from, magically passing through one another and overlapping in space. There's the pushing force, and there's the friction force, which always opposes you. Friction force is perpendicular to the normal force. Normal, what that tells you is that the friction force is always in line with the surface. It's always opposing you. Now, we know from balancing these vertical forces that the normal force has to equal mg here. That's got to be the case. And we know what I'm about to tell you is that the friction force is related to the normal force through mu. Call this force friction. the force of friction is always less than or equal to mu times the normal force. So this is the equation here. Now what happens is you push harder and harder on this block. You push lightly, nothing happens. You push a little more, you push a little more. Eventually you push enough that the friction force would have to be greater than this to oppose you, and it cannot be. So at that point, that exact point, you start pushing the block, and the block moves. So we know that if we balance these horizontal forces here, when you push the block, when you force your push is going to equal mu, which is 0.3, times Fn, which is mg. So if you look at the coefficient of friction, when you're pushing something on horizontal ground, this is the fraction of its weight that you have to push horizontally to get it to move. If you look at this, you end up getting mu times mg. Mg is the weight, so you have to push with this fraction to get it to move on a horizontal surface. That's pretty straightforward. Now, let us go through one or two more complicated examples. What if you had to push a block up a ramp? Call it a 10-degree ramp. The same block. It's clearly a very different block, but we'll say it's the same. Say mu is 0.3, and we'll say mass is 100 kilograms again. We know there's 10 degree here. I want to know how hard do I have to push to get this thing to go up the ramp. Let's draw out the force system again. If you line it up with gravity here, you've got 100 kilograms times gravity down. You have some normal force. You have your pushing force. And you have your friction force. Remember, normal force is perpendicular to the surface, which in this case is sloped, so this is going to be your normal force. And your friction force is perpendicular to the normal force, so that's going to be a 90-degree angle right there. And so you can see these two are in line, this one is perpendicular, and the gravity is the only one that's actually, lined up with this grid. If you get a situation like this, it actually is easier, rather than drawing your little Cartesian diagram like this, you can draw a new Cartesian diagram. You can call up the ramp x, and call this way y. Everything is still going to be in static equilibrium with having x and y like this. Nothing will change. As long as all the vectors point the right directions, everything will be fine and the math will be much easier. So this is how we're going to solve the problem, using this frame right here. We'll draw this thing. Basically, we'll rotate everything so it's easy to look at. And we'll just have to note that the gravity force is this way. This is the gravity force. At 10 degrees, we have the normal force is now perfectly in line with y. The pushing force is perfectly in line with x. The friction force is perfectly in line with negative x. As you can see, the math looks a lot easier already. So, first thing we do is we find out what the normal force is. And that's relatively easy because the only other thing that has to do with vertical forces is this guy. These two don't have any component in the vertical direction, only this guy. So we have sum of forces in the vertical equals 0. So we have Fn plus mg times, and remember that sine is what we use to get the vertical component, provided, remember, if we measure from the positive x-axis. This is 260 degrees. Equals 0. So we plug everything in. We plug in m, we plug in g, we plug in sine 260. That's a simple, we move this term over to the other side. We get Fn equals some number I will not calculate. So we have sine 260 degrees times 100 times 9.8. 965.1 newtons. That's Fn. We know, since we're right about to push the block, we know at that exact moment that the friction force is equal to mu times Fn, which equals 0.3 times this number, which is 289.53 newtons. That's the friction force. Now, the question is, what is the pushing force? If we look at everything that has an x component, we'll work up here. We have sum of forces in the x is equal to 0. So we know that pushing force minus, let's see, this is negative here, 289.53 newtons, plus the horizontal component of this gravity thing, so that'll be plus mg, remember we're using cosine now for horizontal, still have to use 260 degrees, equals 0. So now we solve this. P equals 289.53 minus, let's see, negative 170.17. So move this thing to the other side. Mg times cosine of 260 is minus 170. So when you move that to the other side, you have minus a minus, which is a plus. So 289.53 plus 170.17. The final answer is P equals 459.7 newtons. So, to go over our solution method real quick for block on a ramp. You line up your axes with the block, not gravity, but with the ramp and the block. That way, when you draw all your force vectors, you have your pushing is in line with the x, your friction force is in line with the x, normal force is in line with the y, and the gravity force is going to be down to the left at some angle depending on the ramp. So this will be the ramp angle right here. Do vertical summing of forces to find Fn. Then once you know Fn, you can find force of friction. And then you do horizontal forces to find P. So P has to overcome the force of friction and the horizontal component of the gravity force. Even if there were just wheels, essentially, which means there would be no friction, so this would disappear, you'd still be hard to push this thing up the ramp. So you have to overcome friction and gravity. That's where you get these two terms, and that's how you get your answer. There's going to be one more lecture on friction, and then some final notes to know for the final exam.